So today we're going to continue talking about heat and energy and how we go between phases. So we're going to just summarize kind of endo and exothermic as it pertains to movement of heat in a reaction. We're going to calculate various heats for certain substances, so the heat, the energy, so we call that heat capacity. And then we're going to talk about how we use heat capacity in a laboratory technique called calorimetry. And next week we're going to be doing a lab using calorimetry. So the area of science we've been kind of talking about lately is called thermochemistry. So it's the study of energy in a chemical reaction. So if a reaction gives off heat or takes in heat, it's pertaining to thermochemistry. Now energy, or otherwise called heat, is the ability to do work, or the ability to supply heat. So energy is not considered matter, so it has no mass. It can only be observed by what it can do. So it can increase temperature, it can affect how fast those molecules are moving, or how slow they're moving, but it actually cannot be measured, or it does not have a mass. It's not matter. So something has energy stored in it. We call it chemical potential energy. So potential meaning the ability to release it. And so energy stored is stored in chemical bonds between molecules. And when something goes through a chemical reaction, those bonds are broken and the energy is released. And then we form new bonds, and the energy is taken in to break those bonds. And then energy is released when those bonds reform. So the amount of energy possessed in a molecule depends on what type of atoms are there and how those atoms are arranged. When we talk about energy moving in and out, we have to define what it's moving in and out of. And so we call the system the part of the universe we want to study. So in our case, in chemistry, the system is usually our chemical reaction or the change that we're going to observe. So our beaker with the reactants in it is usually our system. So the part we're studying. The surroundings then are everything else in the universe, the area around the system. There's a law called the law of conservation of energy, similar to our law of conservation of matter. Remember, matter cannot be created or destroyed. So the same thing for energy. Energy cannot be created or destroyed. It can be just transformed, meaning we convert it from one form of energy into another. So it has to go somewhere. So it leaves our system, goes to the surroundings, does something else. But we can't create or destroy energy. Now let's just quickly review our endo and exothermic reactions. So in our exothermic reaction, energy is released to the surroundings. So that means our system, so in this picture, our system would be the fireworks that are reacting here. So energy from our system is moving to the surroundings. So we feel it because we would be in the surroundings. We would feel it as getting warmer. We would be getting warmer. Because energy from the reaction, our system is moving to the surroundings, which is us. And we saw how that looked on our potential energy diagrams. So our reactants were up here. They lost energy to our products. And this amount of energy here, we called it our delta H, was the amount of energy it gave off. So endothermic reactions then are going to be just the opposite. So the energy is going to be absorbed into the system. So in this picture, our ice pack is the system. So it should be gaining energy, and our arm here would be the surroundings. So heat from us is leaving and going to the ice pack, our system. So from the system to the surroundings. So that's why it feels cold to us, because we are losing the heat, and the ice pack, which is the system, is gaining the heat. So endothermic, from the system, or from the surroundings to the system. And then we saw what these diagrams look like. So our reactants are lower, and it gains this amount of energy here being added to the system. So remember, heat and energy are a little bit different than temperature. So heat, when we say heat, we're talking about the energy of our system, the total amount of energy. So if we could add up all those individual molecules and how much heat they possess, we would have the total heat for a container of water. Temperature, though, is just telling you the average energy that these molecules possess. So on average, they have a temperature of 25 degrees Celsius. So heat is the total amount of energy if we add up all the energy from all of us, and the temperature is the average. So for example, if we were to take a poll of our classroom and say, everyone empty your pockets, show us how much money you have. So if we were to add up all the money for our entire class, that would be the total amount of heat or money we would have. But if we took a poll and say on average our class has $1.50 in their pocket. So there are some people that have more than that and there are some people that have less. But on average, this would be the amount of money we have. So that would be considered temperature. So heat is the total amount of energy. So if we add up all those individual atoms, all of their heat and energy they possess. Temperature is on average, what are these molecules at? How much energy do they have? So a question on your homework is going to be, which has more energy? The Rampart Reservoir, which is a big reservoir in Colorado. So Colorado, very cold. Or a cup of hot coffee, which has more energy. So think about that. Think about the last slide we just talked about. And you'll have to answer that on your homework. So how do we measure heat? What are the various units? So one measure or unit of heat or energy is the calorie. Now this is not the nutritional labeled calorie. This is a calorie in science. So energy released in 1 gram of water by 1 degree Celsius is equal to a calorie. When we originally developed the unit, the calorie, and if you look at your nutritional label, like it says maybe, let's see, my granola here has 150 calories per serving. So that's actually 1,000 calories. That's actually a kilocalorie. So if we were to multiply that by 1,000, we would have 150,000 calories in science. So nutritional calorie is actually, they've taken that number and divided it by 1,000 to get a kilocalorie. And they did this because reading 150,000 calories, scientific calories, on a label is very shocking to people. So if you divide it by 1,000, you get the nutritional calorie. But calorie is not a common unit we use in science. We actually use a different, more, the SI unit for a calorie, or for energy, which is the joule, named after James Prescott Joule. So this is the SI unit. This is the unit we will use. So it's a capital J for the symbol, like here next to this number. And so we can relate a calorie to a joule. So 1.48 joules equals 1 calorie. So a joule is defined as the energy needed to exert a force of 1 Newton in a 1 meter area. So let's talk about how much energy we have to add in order to raise a substance's temperature. So how much heat do we need to add, or energy do we need to add? So we call this the heat capacity. So it's the heat needed to raise the temperature of an object or substance by 1 degree Celsius. And we can look up some of these specific heat values, so meaning specific, meaning it's assigned to a specific substance. So it's energy required for that 1 gram of that substance to raise its temperature by 1 degree Celsius. And you can see a bunch of them here. We'll most commonly be using the Joule one. So air, 1.01, aluminum, 0.9, ethyl alcohol, 2.45. So the higher that number is, the higher its specific heat capacity is, means you have to add a lot more energy in order for it to change its temperature. And if you look on this list, water, liquid water, has the highest heat capacity. So water is kind of a unique substance because of the types of bonds and atoms inside of it. it actually has a really high heat capacity. So you have to add a lot more energy to water in order for it to change its temperature. That's why in the wintertime, if you go live next to the water, sometimes it's warmer than inland because, again, it takes a lot more energy to change its temperature. Or in the summertime, it's usually cooler by the beach, again, because it takes a lot more energy to increase the temperature of that water. Right? If you were to walk on the sand, very hot to your feet, and if you go into the water, the sun's shining on them both equally. Why is water so much cooler than the sand? It's because it takes a lot more energy in order to increase its temperature. So if you notice on this list, most metals, like stainless steel, iron, gold, aluminum, they all have very low heat capacities. So they change their temperature quite quickly, right? And that's what we want them to do. Our pots are all made of metals. So metals are going to increase the temperature very rapidly, so it can cook our food a lot faster. So we call those kind of conductors. They conduct heat very well. Things with high numbers like air, water, wood, they're considered insulators. So they like to keep their temperature. So most of our, if you were to take apart like a thermos or a cooler, they're going to have insulators inside of them. So materials like air, or things aren't like this on the list, but like styrofoam, they have higher heat capacity. So they do not like to change their temperature as easily. So you have to add more energy in order for them to do that. So either keeps your food warmer or food cooler for longer. So we can use this value, our specific heat of our material, to figure out what temperature or how much energy our substance has. So we're going to be using this equation. Q stands for heat. So whenever you see Q, that is your heat or amount of energy your substance possesses. And we're going to measure in joules with that. M is going to stand for the mass, so how much of our substance do we have? And we want our mass in grams. C is our specific heat. So that's a unique number you would have to look up on a table, like the one on our last page, or it'd be given to you in the problem. And it has a weird unit. Don't really worry about the unit, but it is joules per gram degrees Celsius. Just the unit, just like saying a joule. And delta T is our change in temperature. So remember, that's going to be our final temperature minus our initial temperature. The temperature we want to be measured in degrees Celsius. Okay. So we can use this equation to get Q, how much heat our substance has. We can use it to find mass. We can use it to get a specific heat, so then we can figure out what our unknown substance may be. Or we can get it to find a temperature of it. So let's try an example. So we have a 100 gram sample of water at 20 degrees Celsius, and we heat it up, so our sample is now 24. How much energy was added? And if we looked on that last slide, we're going to need our specific heat of water. So specific heat of water, or C for water, is 4.18. We're going to see that number a lot, especially on your homework. So we're using our equation. Q equals mc delta T. So we want to find how much energy. So that means we're solving for Q. How much water did we use? That's our mass. So we had 100 grams. Our specific heat, or C for water, is 4.18. And then we want a temperature change. So final temperature minus initial. So we heated it up to 24, so that's our final, minus 20. And then you just want to plug that into your calculator. So I'm going to take 100 times 4.18. And my difference here is 4, so times by 4. And I get an amount of heat as 1,672. And heat is measured in joules, so capital J. So that would be the amount of heat added to heat up my sample of water. Okay. So why do we need to know about heat capacity? So a lot of times we use this in a process called calorimetry. So we can determine if we have an unknown sample. We have tables and tables and tables full of iron has a value of this for its specific heat. Gold has a value of this. So what if we have an unknown metal? So we can use this equation here. We can measure the amount of heat we give off. We have tools to do that. We can measure mass with a balance, and we can measure temperature with a thermometer. So we can solve for C and actually get what is that unknown substance. So we can determine the specific heat of our metal. And so usually we would heat up our metal, and you're going to do this in lab next week. You're going to heat up a sample of your metal to a certain temperature. You can measure that. You're going to add it to a container of water that you know the temperature of. And you're going to see that the water is going to warm up and your metal is going to cool down. And they're going to reach an equilibrium temperature. So a final temperature that's the same. So the energy lost by our metal is going to equal the energy gained by our water. And that process is called calorimetry. So it's an accurate and a precise way to measure how much heat is given off in a reaction. And so if we remember, we said the amount of energy lost by our metal, so the Q, mc delta T for our metal, is going to equal the energy gained by our water we put it into. So mc delta T for our water. So on this left side, we have Q for our metal, and we're losing the energy, so we put a negative sign there, is equal to the Q, the amount of energy gained by our water. If you remember, Q equals mc delta T. So wherever you see the X's, those are your metal's amount. So this is the mass of the metal. This is C, X is standing for the specific heat of the metal. Delta T is the temperature change of the metal. And a lot of times we're solving for C. What is the metal? We don't know. That's what we need to find. Anything with a W after it means the value of our water. So it's the mass of our water. C is the specific heat of our water. And delta T is our temperature change of our water. Okay? So the amount of energy lost by our metal equals the amount of energy gained by our water. We put a negative sign there because we're losing energy in our metal. It's cooling down. So let's try an example. So we have a 55-gram sample of a metal at 90 degrees Celsius. It is dropped into a container of 250 grams of water at 22 degrees Celsius. The final temperature, remember they're going to reach equilibrium, so they're both going to have the same final temperature, is 23.4. What is our metal? So we want to find the specific heat of our metal, so Cx, and then we're going to compare it to values in our table here to see which metal is closest. So let's try this example. Before I start these problems, I like to write out all my variables. So what I have. So mx, mass of my metal, I have 55 grams. Cx of my metal, that's what I don't know. I need to find that so I can figure out what metal I have. My temperature change of my metal, final, which is 23.4, minus initial, which was 90. I can get a number there. So I get negative 66.6 degrees Celsius. Okay, so those are my metal values. So I'm going to find my water values. So water's mass is 250. My specific heat of water, remember, is 4.18. We can look that up on the table if we've forgotten. And my temperature change of my water So my final, remember, they're reaching equilibrium, so 23.4, so same as the other one, minus 22, so it's initial, and I get 1.4 degrees C. So now I'm going to plug those numbers into my equation, my calorimetry equation. So negative mass of my metal, 55, times Cx, I don't know, times by my temperature change, negative 66.6, and that equals the mass of my water, 250, times its specific heat, 4.18, times the temperature change of 1.4. So I'm going to simplify. I'm going to get one number here on my left side. So I'm going to take 250 times 4.18 times 1.4. I get 1,463. Now I'm going to do the same on the other side. I'm going to take negative 55 times negative 66. So my Cx times 3,663. My goal is to get x by myself. So right now I'm multiplying these two numbers together, so I'm going to divide both sides by 3,666, or 3,663 to get my answer. So it cancels over here. And I get 0 point and rounding 40. So remember, I need to find what metal has this specific heat of 0.4. So I'm going to go back to my table. And on your homework I gave you a table so you can compare there. So 0.4, which one's closest? So it looks like probably iron would be my unknown sample, closest to 0.4. Remember, these are experimental data, so they're not always going to be exactly perfect, but they'll be close. Okay, so on your homework, you're going to try a couple more of those problems. So here's what the actual device looks like if you have a nice scientific one to use in your laboratory. So you have your metal sample inside, you have the water container there. So it's a device that keeps it insulated, so we're trying to keep as much of the heat in of the water as possible. But if we don't, we're going to be using our cheap calorimeter using a nice styrofoam cup. So we're going to try this lab next week.